Welcome back, everyone. For this discussion, we will be learning how the cross product can be applied to the real world. So we're going to solve some problems that we see in our everyday lives using the cross product. And we're going to need our tools and understanding that we got from our last video. This slide is a brief refresher on the different properties of the cross product. If you need to go back and rewatch what the definition of the cross product is and how we calculate the cross product graphically, please do not hesitate to do so. And for now, we're going to move on and apply what we learned to some real-world problems. The real-world application we're going to discuss today is something called torque. And similar to the other real-world applications that we've discussed with the dot product and with vector addition, we're going to need to understand what a force is first. In short, a force is an interaction between two objects that may cause a change in those objects' motion, or it may cause those objects to accelerate. So this person here that is pushing on the wheelbarrow is exerting a force on it, and she is changing the wheelbarrow's motion as a result. And a force is a vector. Whenever she pushes on the wheelbarrow more, the motion of the wheelbarrow is going to change faster. That's magnitude. And what if she changes the direction of the push? Will the motion of the wheelbarrow change as a result? And it will. So the push has direction. So mathematically, we can describe a force as a vector. It's something that has magnitude and direction, and we can apply the knowledge that we have about vectors and about the cross product to understand another facet of how forces work in the real world. We've seen force vectors before. The new topic we're going to be discussing today is something called a torque. So let's talk about that. A non-zero torque is created when a force is applied to an object in such a way that that object may rotate. Now you might be asking yourself, well, isn't that basically the same thing as a force? A force is an interaction between two objects that may cause a change in those objects' motion. Before we answer the question, how are torque and force different, we should look at the vector math definition for torque. So up here in the purple box, we define the vector torque as being equal to the cross product between the position vector and the applied force vector. So let's take a look at both of those vectors. The position vector is going to have its tail at the axis of rotation. Remember, a torque is when a force is applied to an object in such a way that may cause rotation. So the position vector has its tail at the axis of rotation, and it has its tip where the force vector is applied on the object. Now the force vector is a real-world vector. It describes something from the real world. The force vector is going to have its tail at where the force is applied to the object. We don't get to choose what the placement of the force vector is. And the force vector's magnitude and direction are determined by the interaction between these two objects. So we also don't get to determine the magnitude or direction of the force vector. So let's revisit this question of how are torque and force different? If the torque vector is equal to the cross product between the position vector and the force vector, are there certain applied forces that will not cause rotation, that will cause a zero torque? So what we're going to do over the next few minutes is look at several different applied forces and see which ones cause rotation, which ones don't, and that will help us illuminate the difference between a force vector and a torque vector. For our example, let's say you're walking through the mall and you see an amazing cookie store with a cookie oven right by the window, and you're just dying to get one of those freshly baked cookies. The only problem is this cookie store has an old-fashioned rotating door. And remember, torque is defined as when a force is applied to an object in such a way that that object may rotate. So the cross product, the application of the cross product to torque is going to be of dire importance in this real world example in determining whether or not you get that cookie. So let's stop for a second to acknowledge that we already intuitively know what the answer to this question is. Much like the real world applications that we've discussed with vector addition and the dot product, you know physics from your everyday lives. You know what the cross product is. You know what the dot product is. What we're doing here is applying the vector math in an explicit way that helps us better understand why what you do when you push on a rotating door, why that works. So let's go ahead and do some examples with this rotating door and see what happens with our torque vector. I've redrawn our rotating door in a way that is going to help us place our vectors. So in our first example here, let's consider that we walk straight at the rotating door and we push directly on the rotating door. So this is our force vector here. Remember, the force vector is placed with its tail where you exert the force on the object. So the force vector is placed with its tail on the outside edge of the rotating door, and we are pushing directly into the rotating door. So in order to do the cross product, we're not only going to need the force vector, we're also going to need the position vector. And the position vector in the cross product is defined as having its tail at the axis of rotation and having its tip where the force is applied on the object. So the position vector for this force vector is going to be this position vector here. Now that we've drawn our position vector and our force vector, we can calculate the torque by calculating the cross product between these two vectors. The first step in doing the cross product graphically is redrawing the two vectors in the cross product tail to tail so that you can sketch in the area that the two vectors span. Remember that this area represents the magnitude of the result of the cross product. So let's go ahead and draw our force vector and our position vector tail to tail. So our force vector pointed directly upwards, so this is going to be our force vector here, and our position vector pointed directly downwards, so we draw our position vector tail to tail with our force vector here. So this is our position vector, and what do we notice about this situation? Remember, when we represent the magnitude of the cross product graphically, we represent it as the area of the parallelogram where two of the sides of the parallelogram are the vectors in the cross product. But we see that if the force vector is pointing directly upwards and the position vector is pointing directly downwards, there is no parallelogram created. Technically, the area they span would be undefined. What we say whenever something like this happens is that the cross product doesn't exist. So what if we calculate the magnitude of the cross product explicitly, like we did in previous examples? So whenever we calculate the magnitude of the cross product, we need the magnitudes of both vectors, as well as the smallest angle between the two vectors, when they are placed tail to tail. If the force vector is pointing directly upwards and the position vector is pointing directly downwards, then on each side we are going to have 180 degrees. So whenever we plug in the angle for the smallest angle between the two vectors when they're placed tail to tail, it's going to be 180 degrees. So let's go ahead and do that. The magnitude of our cross product is going to be equal to the magnitudes of our vectors multiplied together, multiplied by sine of 180 degrees, and sine of 180 degrees is equal to 0. So the magnitude of the cross product is equal to 0. Remember that torque has the physical interpretation of when you exert a force on an object in such a way that it may cause rotation. So this torque has a magnitude of 0. It is a 0 torque. That means there is no rotational motion. By applying the force vector to the door in this way, we are not going to cause the door to rotate. And we see why force and torque are different. This force right here exists. It's real. But even though the force vector is real, has a non-zero magnitude, the torque vector doesn't exist. No rotational motion is caused when you apply the force in this way. Let's engage in some good old-fashioned trial and error. Basically, what you would have done as a kid. Remember, you already know what a force, what a torque, what a cross product is. You developed this physical intuition for how the world works whenever you were much younger. All we're doing in this class is giving you the mathematical tools to understand that on a deeper level. So, let's apply a slightly different force to the door and see if we get a non-zero torque. So our force vector this time is going to be applied in the same place on the rotating door, and we're going to be pushing on the door at an angle, not directly into the door. So our force vector is already drawn up here. Remember, our position vector has its tail at the axis of rotation and has its tip where the force is applied on the object. So our position vector is going to be the same as the one that we had before. So this is our position vector here. Clean that up a little bit. And we've drawn our position vector and our force vector on our diagram. We can now do the steps of the cross product and see what happens with our torque this time around. So let's go ahead and calculate the cross product for our new force vector. The first step in calculating the cross product graphically is drawing the vectors tail to tail and using them to create a parallelogram. The area of the parallelogram represents the magnitude of the cross product. So our force vector is going to look something like this. So this is our force vector, and our position vector is going to look something like this. So this is our position vector. We want to draw in the other two sides of the parallelogram. So we draw in the other two sides here, and we shade in the area of the parallelogram, and the area of the parallelogram represents the magnitude of the cross product. So this parallelogram exists. It has an area that can be defined. And as a result, we know that the cross product exists as well. What we want to do now is calculate the magnitude of the cross product explicitly. So doing the parallelogram method gives you an idea of the magnitude of the cross product, but we want to calculate it explicitly because this is more precise. So the magnitude of the cross product is the magnitude of the first vector multiplied by the magnitude of the second vector multiplied by the sine of the smallest angle between the two vectors whenever they are placed tail to tail. Whenever we drew our force vector on the previous slide, we had the angle 35 degrees measured with respect to the horizontal. So this angle here is going to be 35 degrees. We want the smallest angle between the two vectors when they're placed tail to tail, which is going to be this angle here. To get that total angle, we have to add the 90 degrees right here. So the smallest angle between the two vectors when they're placed tail to tail is 35 degrees plus 190, plus 90 degrees. I apologize. So if we simplify the sine of the smallest angle, we get 0.82. The magnitude of the position vector and the magnitude of the force vector are non-zero. They have real lengths. And this is the magnitude of the cross product calculated explicitly. Now we know the magnitude of the cross product. The next thing that we need to do is determine the direction of the cross product. So remember, in the cross product, we put the first constituent on our pointer finger, the second constituent on our middle finger, and the resulting vector, which in this case would be the torque vector, on our thumb. So we point our pointer finger in the direction of the position vector, which is downwards. This is difficult. And then we point our middle finger upwards and to the left, which is in the direction of the force vector, and we get the resulting direction for the cross product is into the board. So the direction of the cross product is going to be into the board, and its magnitude is going to be this. For our last example, again engaging in some good old-fashioned trial and error, we're applying a different force to the door to see how it changes the torque. So this force is applied in the same position on the door, but you're pushing directly to the left in this diagram. We want to draw in our position vector so that we can calculate the cross product. So our position vector has its tail at the axis of rotation and its tip at where the force is applied on the object. So let's calculate this cross product and see what has changed. The first step in calculating the torque vector graphically is drawing the constituent vectors tail to tail so that we can sketch the parallelogram whose area represents the magnitude of the torque vector. So we have our two vectors drawn tail to tail here. We sketch in the other two sides of our parallelogram, which just so happens to also be a rectangle, and the area here represents the area of the torque vector. We see that the area is non-zero, so the torque must be non-zero as well. So let's go ahead and calculate the magnitude of the torque vector more explicitly. The magnitude of the cross product between these two vectors is equal to the magnitude of the first vector multiplied by the magnitude of the second vector multiplied by sine of the smallest angle between the two vectors whenever they are placed tail to tail. And if we go over here and look at our two vectors, we see that the smallest angle between them when they're placed tail to tail is going to be 90 degrees. We simplify, the sine of 90 degrees is going to be equal to 1. So the magnitude of our torque vector is going to be the magnitudes of the constituent vectors multiplied together. And this is a very special case. We're going to talk about why. First, though, we should determine the direction of the resulting torque vector, Remember, the cross product outputs a vector, so we need magnitude and direction. We place the first constituent, or the position vector, on our pointer finger. We place the force vector on our middle finger, so we have our pointer finger pointing downwards and our middle finger pointing to the left. And we once again get that the thumb, the resulting torque vector, points into the board. So what I want to discuss here about these different examples is how we already knew the answer to these problems. In our first example, we saw that pushing directly into the rotating door caused no torque. It caused no rotational motion. In our second example, we push on the rotating door at an angle, and this caused rotational motion, but it didn't maximize the rotational motion. You maximize torque, you maximize the cross product whenever the two vectors are at right angles to each other. So the smallest angle between the force vector and the position vector was 90 degrees. And you intuitively know this. In order to maximize the change in rotational motion, you have to push at a right angle to the rotating door. You have to push at a right angle to the position vector. Whenever we do vector examples and vector math in this class, all we're doing is giving you the mathematical tools to better understand the physics that you already know from the real world. Let's just recap what we learned today. The cross product, our new vector operation, is something that is used in the real world all the time to calculate changes in rotational motion. Our example that we did today was the rotational motion of a rotating door, and we saw how different force vectors exerted on the rotating door caused different torques. They caused different changes in rotational motion. So we saw a zero torque that caused no change in rotational motion. We saw an in-between torque that did cause a change in rotational motion. And for our final example, we saw a maximized torque that caused the maximized change in rotational motion. So just to stress and reiterate, what we are teaching you in this class has implications for understanding the world around you.